All right, let's keep it going. Next up is section 1.3. This is going to be talking about barriers. So this is going to be our skin and our mucosa. Let's start with the skin. We already kind of broke it up into the regions on day one, but we have the epidermis, the dermis, and the hypodermis. The epidermis can then be subdivided into the stratum corneum and a couple other layers. Excuse me, I'm only worried about the stratum corneum, and that's right here, stratum corneum. That's the outermost layer, the outermost layer of the skin. That layer is composed solely of keratinocytes. That's the main cell in the epidermis. Those cells are going to produce something called keratin. Keratin is a strengthening compound that makes our skin more protective in nature. Okay? So that keratin is going to do a couple things. A, it's going to protect us, but it also kind of shunts water out of these developing skin cells. So this top layer is actually dead. And that's why, I don't know if you see, like, if you ever scratched your arm and the sunlight's hitting it really well, you can see those skin cells just flying right off. And that's because that top layer is technically dead. So it's constantly getting shed, constantly turned over. But that's great. That means we have a constant supply of fresh cells that are providing our protection. Okay? Then a more active role, we have our Langerhans cells, which are specialized dendritic cells that are hanging out in this epidermis, and they're waiting to detect any potential pathogens that might enter through some abrasion. Okay? So they capture local antigens and then go and present them to the lymph nodes. Okay? So these are our innate cells going to present to our adaptive cells. Think about what adaptive cells we would go present to in the lymph nodes. That's going to be your B or T cells, okay? Depending on whoever gets activated. Then in the dermis, we're going to mostly have macrophages. This is where they like to hang out. Again, they're very phagocytic. They remove debris, and they're also pretty good at signifying to other immune cells that there's an infection going on. You know, obviously not nearly as good as like T helper cells, but they are still pretty good at recruiting. A cool fun fact, your macrophages in your dermis, they are removing debris. Tattoo ink is considered debris, but it's not like pathogenic or anything, so the macrophages that pick that stuff up just hang out there, and that's where you get your tattoos from. So I think that's pretty cool. If we scroll back up, the pink area is the dermis here. So that's like the majority of the skin. That's where all your accessory stuff is hanging out. So this is a hair follicle and a sweat gland. So that's where the dermis is. And I'm not too concerned about this, but you do have mast cells hanging out in the dermis as well. And that's where, situations like hives and allergic reactions that are associated with the skin. We have that histamine response, increasing blood flow, vascular permeability, and excess of white blood cells. Now, this can be really helpful if infection is actually occurring and we need more soldiers on the front, but typically mast cells are associated with an allergic response when we don't need that much inflammation in the region. But those can also be found in the dermis as well. All right, in terms of chemical defenses, you have your acid mantle. Your acid mantle of your skin is just the idea that there's a thin and slightly acidic film on the surface of your skin composed of sebum and sweat. So one of my things, I really like to have my electronics clean and no smudges on my screens, but invariably I'm going to have some. And that's because anytime, like if I wipe something off on my screen, well, there's always going to be a thin layer of oil on my skin, no matter how much I've been cleaning my electronics or my hands. That doesn't make me dirty. That's just part of my skin's physiology. And that acid mantle is actually really protective. It creates a pH of about 4.5 to 5.5, which is pretty acidic, and that's very good at defending against bacteria. And that sebum and sweat have antimicrobial properties. The sweat contains AMPs, which is great, and sebum contains fatty acids, which are also antimicrobial and hydrophobic, meaning they're afraid of water, and most living things have some sort of water component to them. So both of those are helpful at dissuading bacteria. Something to note, overwashing can actually end up disrupting this mantle. So if you've ever seen a case of maybe someone has a compulsory overwashing their hands problem, that's a thing that can happen. Their hands become very, very brittle and cracked, and you start to expose your skin to more pathogens because you're kind of removing that natural physiological barrier that the skin is creating for you with this acid mantle. Obviously, not to say you shouldn't shower. I'm not saying abandon hygiene, but there is something to be said about the natural defenses that the skin can produce for us, which is pretty cool. But yes, please still wash your hands. Another cool thing is the microbiome. So the skin hosts billions and billions of bacteria that are either harmless or beneficial. And even if they're harmless, so like some maybe make some compounds for us that help with defense, maybe some antimicrobials, maybe something like that. But even if they're harmless, even if they do nothing, they do compete for space and for nutrients. And that's a really cool concept because let's say something toxic does come across your way, but there's just no room for them. That's great. If you want to think of us as a landlord, a tenant that brings us cookies, that would be awesome. But a tenant that doesn't give us any problems, that's quiet, that minds its own business, that's also more than welcome with us. So that's another concept with our microbiome. And it can also secrete compounds that deter other bacteria. Right? I think that's where penicillin comes from, was just a bacteria secreting antimicrobial peptides to get rid of competing bacteria. That can also be a beneficial case of your microbiome. Okay, that's the skin. We'll press on to the mucosa. So the mucosa, when I say that, it's referring to the idea that there's a lining of the organs that open to the external environment. Okay? So a great, easy example, think of your digestive system. Right? Yes, that all of this is contained within your body cavity, but if you think about it, the mouth would be like, right up here. Oh, that's nasty. And then your esophagus, stomach, all of this is small intestine, and then large intestine. So yes, there are barriers and borders here, but this whole tube is open to the outside world. So you have special barriers in place that regulate this and also carry out whatever function that organ is meant to do. So as you can imagine, the digestive mucosa is probably going to help with nutrient digestion and absorption. And that'll make itself apparent as we continue on here. So other examples would be respiration, the urogenital tract, as well as the ocular mucosa. So the eye is an example as well. Each consists of an epithelium, a basement membrane, and a lamina propria. I'm really only concerned with the epithelium here, because the epithelium is what's going to dictate function. All right, let me get rid of this shoddy drawing. I'm going to do it again. Okay. So if you imagine I take a cross section anywhere in this tube. So I just said this whole thing is one continuous tube, but somewhere, some way, I can take a cross section of this tube. All right, and that's what I'll get. Just a tube. In the middle of the tube, let's say I just cross-sectioned like the stomach. Well, I'll have like a pool of stomach acid, right? Maybe a chicken wing, a chicken leg getting digested. Something like that, whatever. Obviously not drawn to scale. And then the layer of cells that's facing the lumen. So that's what's, when I say lumen, if I haven't made that clear, the lumen is just the space that stuff is happening in. So in the digestive tract, the lumen would be the space in which digestion is happening in. The cells that are facing that space, that's the epithelia, or the epithelium. All right, so in this case, this is, we'll say, stomach epithelium, and that's going to help us secrete compounds that break down food. If I were to draw a respiratory mucosa, well, that epithelium would consist of things that help me breathe in air. All right? So that's just the concept I'm after here. The epithelium is going to dictate the function of whatever organ we're talking about. The basement membrane, the lamina propria, those are basically just the glue that holds these tubes in place. The basement membrane is the glue, and the connective tissue, the lamina propria is that connective tissue holding things in place. Not really worried about that. That's just the whole idea of mucosa. But the epithelium, that's where the function comes into place, and that's what I like talking about. So the mucosa is always moist, always mucus-coated. It sounds kind of gross, but it's really, really helpful for us because mucus has a lot of excellent properties. Mucus is produced by goblet cells. So I kind of drew another epithelium here. This one's just a bit more long, more rectangular. And interjected throughout the various mucosas are goblet cells. They kind of look like this. They are said to, look like chalices or goblets, like the goblet of fire. And they're chock full of mucus. Chock full of mucus. So they are constantly secreting that onto the membrane because mucus has a lot of beneficial compounds. Concepts to it. It can trap dust. It traps microbes and debris, act as a lubricant. So just think of that goop. I know it's gross to think about, but secreting mucus is one of your body's most natural responses to almost anything. Anytime you have an illness or anything, that's just one of your body's defenses because it does have a lot of helpful properties in terms of getting things that aren't supposed to be there out. It also contains antimicrobial peptides and is constantly being renewed, which is, again, it's good. It's not stagnant. Like you don't want still water ever. You want constant renewal, and that's something that our goblet cells making our mucus does for us. All right. So I kind of hinted at that obviously the different regions of the GI tract are going to have different functions because that's what makes organs different. But the epithelium is what's going to dictate that. All right? What do I mean by that? So some regional specialization. Let's talk about that. So the mucosa of the respiratory tract, it has a really specific epithelium. And that is called pseudostratified ciliated columnar epithelium. I know, that's a mouthful. I'm sorry. You're more than welcome to use PCCE as an abbreviation. PCCE. All this means is pseudostratified means it looks layered, but it's not. So in this drawing right here, if you were to zoom out, it might look like it is cobbled. That's what a actual stratified epithelium would be. But if you zoom in, you'll see that actually it's not cobbled. These cells are just wobbly. These cells all make it all the way down to the basement. So they are not technically stratified. Really, I'm not worried about that, but if you wanted to know what that meant, that's what that means. I'm more worried about this. Ciliated. So you'll see in my beautiful drawing here, I drew little hairs hanging off on top of the cells. These are immensely important, especially in this respiratory tract here, okay? Because they are going to contribute to something called the mucociliary escalator. Mucociliary. So I just got done talking about how awesome mucus is, and cilia are just as awesome, especially working alongside mucus. So let's go back up here. All right. So let's say this is the level of my windpipe. Mouth is up here, lungs are down here. So this is where, in my lungs, this is where gas exchange is occurring. So O2, CO2. All right. If we want that to occur, right, those are atoms. That's fundamental particle level. Very, very, very small. I don't need big clumps of mucus blocking that. If we're at the atomic level, that blocking could be really easy to occur. So what happens is that mucus that is trapping debris, trapping microbes, as it's making its way down, the cilia, the little hairs hanging off on this epithelium, are actually beating upwards, waving their way upwards. So any mucus that gets trapped in them gets slung on up back to the oral cavity. And that's what I've kind of drawn here. Maybe let's go ahead and let's do this. Ew, there we go. Now it's all mucusy. Perfect. So we're shunting that mucus back up from the lower respiratory tract, back on up, 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 until we get back to the oral, the pharynx region. So that cilia beats us rhythmically, all that mucus, all that debris, all the way up to the pharynx. And now we can expel it or swallow it. Kind of gross when you say it out loud, but that's the idea. You either do a huck tui, or you send that mucus down to your stomach where that high pH can take care of it. What's really interesting is we've found over the years that the mucociliary escalator is absolutely slammed by smoking. Now, it's not a permanent paralyzation by any means, but it is certainly impaired by even just nicotine in general. So, chronic overuse or chronic smoking is going to impair this physiology, and you could probably hear it if you know a chronic smoker, maybe like an older relative, and they have that deep barrel cough where they just can't seem to get that phlegm out of the way, and that's because these cilia are just completely not doing their job anymore. So something to consider. Then you have your dust cells. So let's say something does make it all the way down to the lungs. At the lowest portion of the respiratory tract, or actually let's do this. The lowest portion of the respiratory tract literally looks like grapes. Oh my goodness. There we go. These grapes are your alveoli. Oh my goodness. Can you work with me here? Okay. And this is where gas exchange is occurring. It's at the bottom level of the lungs. You can imagine, though, if we got debris down here, well, that would be bad. That was the whole point of the mucociliary escalator, to get that mucus all the way out. But invariably, something might pass that cilia and get down to the alveoli of the lungs. So we have dust cells stationed down there to get rid of anything that makes its way. So dust cells are literally just the macrophages that are in the deep lung to ensure that gas exchange is still occurring just fine. All right, now on to the GI mucosa. Almost done here. It's usually just this easy, simple columnar form. We'll have some goblet cells probably thrown in there too with the mucus and stuff, but the GI is typically this simple columnar here. And we have our stomach with a specialization here, hydrochloric acid. So if you've ever heard of stomach acid, I'm sure you probably have. It is literally just hydrochloric acid, giving us a pH of about 2 to 3, which is really, really acidic. So that's going to destroy most microbes. At the same vein, we kind of get the best of both worlds. The stomach lining does not want to get damaged by this HCl, so much of the stomach lining is going to produce bicarbonate. Bicarbonate is a very basic compound. I can write it out. I don't remember much of my organic chemistry, but it is a very basic compound. So it kind of equalizes out the damaging nature of HCl without disrupting the physiology that's occurring in the stomach space itself. So there's one benefit of the GI tract. Another benefit is the small intestine. The first thing is villi and microvilli. So if I go over here, this is my drawing of the small intestine, and you're going to have these projections that kind of stick up. So this is where food would be going. Okay? And you have these little fingers, sticking up into the space where food is going. Furthermore, if I were to zoom in, on the fingers are even little more fingers. Or even more little, I don't know. You know what I'm trying to say. Another subsection of fingers. And those are called microvilli. The whole point of that is to increase our surface area. Okay, the more surface area I have, the more stuff can happen there. All right? So that's a advantage of the small intestine. And you also have some cool immune outposts here. So bear with me. The green we'll talk about first are your Paneth cells. Paneth cells. These guys are really easy. They are basically just bacteria regulators. Regulators. Oh yeah, there it is. It lines up perfectly. They regulate the microbes there. Okay, so obviously with the microbiome, you're going to have a bunch of bacteria hanging out here that might be doing helpful stuff for you. And if they're not secreting any toxic compounds, then that's fine. But if there is any toxic compounds being secreted, then your Paneth cells can detect that. Or if maybe your helpful bacteria are just getting too populous in nature, then the Paneth cells can say, hey, all right, tone back, I don't need that many of you. So those are your microbial regulators. Then you also have something called M cells, and the M cells are going to feed into your Peyer's patches. So those are two fun words there. So let's look at that. So at the tops here, we'll have M cells, and those are going to detect things that are floating in the tube, uptake, and transmit them down to this little outpost here. This outpost, this is the Peyer's patch. We'll just go peep. The Peyer's patch. And that Peyer's patch is an example of that GALT, that associated lymphoid tissue. Okay, so basically what this is just an outpost of B and T cells. And some other helpful immune cells as well. So let's look at that through a different lens. So that M cell, so here are just the various nuclei of the M cells, or of the surrounding cells. This one is the M cell, mostly I'm talking about here. And let's say you have some antigens, some nasty bacteria or something. This M cell has a cool pocket in it, a cool pocket that takes whatever bacteria it's come across, brings it to an antigen-presenting cell, and that immediately gets delivered to these guys here. And these are just some B and T cells that are waiting in the periphery. So this is a perfect example of that MALT, that mucosal-associated lymphoid tissue. We just have outposts and checkpoints hanging out everywhere, and this M cell Peyer's patch combo is a great example of detecting that. So we'll come back to that in another lecture, I'm sure, but that's a really good combo to know, the M cell Peyer's patch combo. All right, and next up we have the microbiota. I've already kind of referenced this. We'll talk about this a lot in the next chapter. We have so many commensal microbes that are present in the gut. Again, competing for resources, so anything toxic hopefully gets competed out of contention. And they also produce vitamins for us, which is great. And some of them have even learned to secrete compounds that select for regulatory T cells, which is awesome. Those regulatory T cells, like I referenced in the last video, they select for a less inflammatory tone. And that's very helpful for preventing any autoimmunity, preventing allergy, preventing overreaction to things. So, and that includes any potential commensal microbes. like, yes, they are bacterial in nature, but if they aren't producing any toxins or if they aren't harming us, then we need to know not to fight them because they could potentially be helping us. So selecting for Tregs is a pretty cool concept that these bacteria have selected for. All right, last little bit here. We'll talk about the genitourinary. A lot of this is pretty self-explanatory. If it's the urinary system, you can imagine that's pretty acidic. I don't remember the pH off the cuff. I'll say it in class. We have regular flushing. Obviously, you pee probably a couple times a day. That's going to clear out microbes. So that's just a physical functional benefit. On the repro side of things, for female reproductive system, obviously the vagina is a very acidic environment, and we have those resident microbes that convert glycogen into lactic acid, again maintaining that acidic environment. So that's awesome at deterring at least foreign bacterial invasion. And then you also have the mucus plug that's sealing off the uterus, hopefully preventing any further invasion up the female reproductive tract. In terms of the male reproductive tract, in seminal fluids, that's, I guess, the liquid component around the sperm. So that's not just the sperm in an ejaculation. You also have fluid that, I guess, helps maintain or gives energy to the sperm, and that has antimicrobial peptides in it as well. So you can see that this defense mechanism is all throughout all of our systems. I already gave us a really good example of malt with the M cells and the Peyer's patches, but generally speaking, they're just immune cell clusters in mucosal tissues. Again, outposts for surveillance, and this gives us a local response as opposed to sending a command in the blood where I have inflammation everywhere. And those are the major types: Galt, Balt, Malt, Galt, Balt, Nalt, and Gualt. So that's just GI, bronchial, nasal, and genitourinary. You don't need to know these. It's not. It's really not a big deal, but just to give you the full picture, if you ever see anything with that alt, especially in this context, in this immune context, that's what it's referring to. And there's probably even a couple. I think there's probably O-alt for the ocular area too. So there's just a bunch, but that mucosal associated lymphoid tissue, this was a really, really great example of it. You just have outposts stationed throughout your mucosa that are ready to detect things that might not, instead of detecting things in lymph nodes or detecting things in the spleen and in the blood, if I detect it in a more localized manner, well, I can probably handle it in-house without triggering any body-wide inflammation. Another cool concept of that, sometimes you can have T cells that are just residing in the epithelia. This is pretty rare, but you do have intraepithelial lymphocytes, or IELs they're called. Again, just T cells that have some panache and just want to hang out on the front lines. Another really cool thing, so on the last lecture I talked about B cells secreting antibodies. Anytime you see IG, think about antibodies. So IG stands for immunoglobulin, and then the letter after immunoglobulin is the type of antibody it is. In this case, we have A, IgA. IgA is secreted into the mucus, and it is always on mucosal membranes. It's another level of defense. So that's part of that antimicrobial nature of mucus, is that it has IgA. And we talked about IG, or all of our antibodies like to bind pathogens. I'll give you. So there's a little bacteria getting bound by IgA. And again, another example of if it's systemic, if it's localized, then I can get rid of this infection without triggering body-wide systemic inflammation. IgA is cool because it always forms in this double formation. This is called a dimer. A dimer. So IgA always looks like this. In fact, if it gets chopped, it doesn't work as well. All right, and it's also very abundant in saliva and tears. So we have these compounds everywhere really trying to help us out. That went a little bit longer. I'm sorry, folks, but that is all of our barriers and kind of how that functions for us. So thank you very much for listening, and have a wonderful day.